Hello everyone. Hello Dinesh. Hello Phoenix. Hello Saurabh. Hello Arpit. Hello Vishal. Hello, good evening. Okay, so we shall be starting in 2-3 minutes. Let everyone join in. Hello Aarti. Hello Dark Lord. Hello everyone. Uh, till then, you can um, you can try to think of that minimum path sum problem. Hello Shubham. Hello Saloni. Hello. Good evening Debajyoti. Good evening Vidya. You guys can till then try to think of an approach for this minimum path sum problem we were doing in the last class. Share my screen. This was the problem we were looking at. I guess after looking at this problem, it's quite clear that um, we have to use 2D DP in this, right? Like such problems, I feel like where they have already given a grid, you kind of think that at least there will be a 2D DP used here. I mean, that's how I feel looking at such problems. I feel like uh, the biggest hint for this problem is written here only, right? Okay, Devajyoti says I solved it by. Yes, you are correct, Devajyoti. That's the correct approach. You are thinking in the right direction. Okay, so let's start the today's session. So, hello everyone. Today is day 3 of this bootcamp. Today we'll be trying to solve some really good problems and famous problems of dynamic programming. We'll be doing some problems on 2D DP plus subsequences, and we'll be also be introducing ourselves to DP on strings. We'll be doing some problems where we use dynamic programming on strings, so it will be fun. today. Long. Arpit, it's very nice that you are taking care of the integer overflow issue, but I feel like in this problem, the constraints are not that high. So it will be fine if we use int. But yes, you are right that even your approach works even if the constraints are more than 10 raised power 5 here, 10 raised power 10 raised power 5, 10 raised power 7 here. Okay, so let's try and solve this problem. Is my screen visible to all? Uh, just a second. Yeah, just a second, just a second. Hello, good evening, Vishal. Good evening, Lalit. Um, I am not. Am I audible to all? Navlit says I'm not audible. Yes, Akshita, your approach is correct. Okay, I'm audible, right? Yes. So let's start with this one. I hope that every one of you should have thought 2D DP approach. Uh, is there a confusion to someone that why is 1D DP not applicable on this? Is there a confusion of any kind that why we are coming to the conclusion that we should be able to think of 2D DP while looking at problems which involve grid, 2D grid or something like that? Is there any confusion? I hope that my screen is visible to all. So let's start. Minimum path sum is the problem we are trying to solve. So it is quite, we have done edit distance problem in the last class, right? This is quite similar to that. Let's break. We need to find the minimum path sum to reach here from here, from source to destination. What's the minimum path? And the constraint is you can, from a point, you can only go down and right. So we can code our solution for this one. I realized that screen was stuck. Maybe now I guess it's visible to all, right? So Let me fix this issue first. I guess my screen is getting stuck. A lot of times. Till then, you guys can try to solve it. I have given you a hint that you will be using 2DDP in this problem. I hope that it is fixed now, the issue of the video. Let's just quickly jump onto the problem. So first I'm trying to the base cases, trying to define the base cases for this problem. Okay, now it's, I hope now it's decent. Okay, so we are doing it in the same way that we did edit distance problem, right? First, we define the base cases for the first row and then for the first column, so that because they were easy to define. dp of 0 comma 0. This is trivial, yeah, right? This condition is trivial. In order to get to the 0 comma 0 cell, uh, the answer is g of 0 comma 0. I hope it's trivial. Um, so what we're trying to do is we're trying to mm, define base cases for these rows, so that because what we need for any arbitrary cell, we want to ask a question to this cell: what was the answer for you and what was the answer for you, and we need to take the minimum of those and then add this, right? I hope it's clear to everyone that we are defining our um, we are defining our transition function as this: -1 plus g of I comma j. I hope there is no doubt in how we are I hope it's visible to all now. So we are trying to code it out. Oops, this should be okay. I apologize for the issue on my end. I guess it's a network error. Let's continue. I guess my screen got stuck while I was writing this part of the code. Um, right. Mm, is it? I hope now it's clear. We should proceed with the next part of the code. I already explained why this transition was needed. I'm just coding it out. You guys can also code on your machines. Uh, dp of I comma j is equal to minimum of dp of I minus 1 j comma dp of j minus 1. I think this should work. Yes, it works. Yep, and it passes all the test cases. Is there any doubt to anyone how we have come up to the transition function, how we are writing the base conditions? I can explain it. I understand that there were many interruptions due to network in this question. So I will entertain every doubt if you have any doubt in this problem. Like, what was the approach? How many of you want me to explain this again? I understand that there must be a uh, interruption due to network. Is it clear to all how we have come up with this answer? Some of you uh, were able to solve this by yourself, but I guess some were not able to. So just tell me. I will repeat it again. If, okay, I will explain it. Okay, Suruchi, I will explain it once. Um, so the core idea is that we need to get uh, the core idea is that we need to start from the source and get to the destination into uh, the minimum path sum. So, and you can, there are two constraints. You can only go bottom and right, and you cannot go out of this grid. Okay. So, if you would have reached some I comma j grid, it is obvious that you might have been at the top or you might have been towards the left. From there only you would have approached this cell, right? So, what's the greedy approach of it? To reach this, you need the answer for this and the answer for this. Just imagine that you have processed this much of the grid. Now you are processing this. You have answer for this, you have final answer for this. For this, you need a minimum of them and then add g of I comma j. Does it make sense? Okay, so does it make sense why the greedy approach works? Assume that you have solved it for this portion of the grid, and then then you need answer for this. You just need minimum of this part and minimum of this part, and then the minimum of those you add with the value, and then you get the answer to reach here from here, right? And the base case are for here, the answer is this only because this is the first cell. And for this column and for this row, the answer is simply for this, the answer is addition of these two. The answer for this is the addition of these three. Because, see, simply, there is only one way to reach here or only one way to reach here. Because there is a constraint that you can only go towards, you can only go downwards or towards right. So you can have something like this, you can have something like this, you can even have something like this, you can even have something like this, only bottom and towards right. Yes, okay. So that's how we come up with this transition function. And the base conditions are pretty simple. Like base conditions are pretty simple because base conditions are inspired by the constraint they put on this problem that you can only go uh, down and right. Okay. The base conditions were this. And you know what? Base conditions help us to actually relax our implementation of this. Because see, when you are implementing this part, you ideally you should be careful if I minus 1 ever becomes less than 0. So then it gives segmentation fault. We have encountered segmentation fault in the first class, remember? When I guess someone asked why you are putting it n plus 2, I plus 2. So you need to keep in mind that whenever doing I minus 1, you can get segmentation fault, but you will never get segmentation fault. Why? Because you have already processed this part and now you are running your loop for this. So I minus 1 and j minus 1 will never go out of the bounds. Understood? Like just how I have done here. See, I have cleverly started my transition function loop from 1. I was able to do this because I already initialized the base case for the first row and the first column. Understood? I hope now it's clear how we have um, computed the solution for this problem, how we have coded this problem, how we have come up to the transition function. Is it clear? If it is, then we move on to the next problem. And if you have any doubt, then please ask me in the chat. I feel like it's clear to everyone. So let's move on to a very popular problem, longest increasing subsequence. Mhm. How many of you already seen this problem? This problem is pretty famous, and it's used in like a lot of other problems as well. Like longest bitonic sequence, you would have seen. LIS is used in many problems. Hmm. Yes, Bhavika, you would have seen this in many other problems. If you guys would be familiar with the code forces and all, then competitive programming, there are many problems inspired by this problem, right? So think of an approach for this problem. Longest increasing subsequence. Like, see, till now we have solved the problems which were quite straightforward that they will be solved by 2D DP. Uh, but now we will see some problems which are not that obvious if we need to apply 2D DP here. And like you are not expected to think a solution for it if you are seeing it for the first time, right? It's just a pattern, it's just an introduction. I'm introducing you to a pattern. So let's begin. I hope everyone has read that problem. So longest subsequence, oh sorry, longest increasing subsequence, longest increasing subsequence. So the idea in this problem is pretty simple. Let's say you have an array. You have an array A, we call this array A. You are processing for some jth, or maybe not jth. You are processing for some ith value. So this is the construction of the problem. You define dp of I as lis ending at I. Think of it like this. Think of like constructor dp array like this. You need only a one. This is a 1D dp problem, but this will be solved in n square. Like the best asymptotic we have achieved in this is n log n. That solution requires binary search, but try and uh, try to construct a solution around this definition of dp array. Now, if you think closely, then longest increasing subsequence ending at I. So ideally, if you find any smaller value than present here, then you will greedily add it in your count, right? But you cannot always add it greedily. Why? Let's say, let me give an example of this. 200 10 9. Now see, if you simply add 2 in your subsequence, you get 2 and 100, then you can not add these two numbers. and this is your longest increasing subsequence ending at 100. Ideally, this would have been your longest increasing subsequence, right? So clearly the greedy approach does not work here. Clearly the greedy approach does not work. So what we do is, for every I, we again ask the same question to this. What's the longest increasing subsequence for you? And if it says some x value and this a of j is less than a of I, then we can simply add this to the answer for this can be added to answer of this plus 1, because whatever longest increasing subsequence we would have reached ending at this, we can extend it to this, right? Because this value, if this value is bigger, if and only if this value is bigger, right? If and only if this value is bigger than this value, you can add its result to this one. So by this construction, we can solve this problem. I will solve this problem like this. Yep, it passes the test cases. It should accept, and it accepts. So is this problem clear to all? Is there any doubt? Don't stress about attendance. We will eventually share it. I hope it's clear. If there is any doubt, then you can ask it in the chat. Is my solution correct? What was the solution, Arpit? I guess I missed it. You can You can mention it again. Is there any doubt to anyone in this problem, or shall we proceed? Yes, Debajyoti, you can optimize it, but that optimization doesn't require DP. That optimization requires binary search. You can search for just see the nlog and optimization of this problem. Like, look at this. The follow up actually asks you to compute the answer in nlog. Then next, how we initialize the array, size of the array. The size of the array is equal to the size of the input array. I mean, I hope there is no doubt in that. Is there any other doubt in this problem? The code with the examples. Yes, yes, I can explain that for sure. As it is n square dp, I will take a small example. Uh, let's just take uh, the example of 1 3 4. Oh, monotonically increasing. 1 4 15 3 10. Okay, so that's how you will go. First, you will be at this. The value will be 0. The value will be 1 1 1. You will process this. Nothing will change. Then you will process this. You will see 1 is less than 15. 1 is less than 15. So you will add the result of 15 into this. So you will do this. After processing 15, you will come at 3. You will compare these two. This is greater, so you will not do anything. Then you will compare it with this, putting up a pointer like this. For every I, you are going in this direction. So you see this is smaller than this. You add its result. So in this iteration, it becomes this. Oh, it becomes this. Now you come to this. You check this is smaller. So you add its result plus 1 to this. Result is 2 plus 1. You do 3. And now you just pick the maximum value out of this, just 3. So you output 3. And clearly the output for this is 1, 3, 10. Right. The attendance link is in the chat. You can mark the attendance for today's session. Can we use built-in binary search, or we have to write the binary search from basic? You can use built-in binary search. There are functions like lower bound and upper bound. You can use them. Okay, so I hope that this longest increasing subsequence problem is clear to all. Let's just quickly uh, jump on to this problem of longest palindromic subsequence. What shall we do first? Longest. Hmm, let's just do longest common subsequence. Okay, so the next problem is longest common subsequence. You will get two strings t1, t2, and they will be EF, GH, BB, DEF, S. You will get two strings. You have to give the maximum longest common subsequence in those two strings. In this string B, D, E, F, G, H. Clearly, the answer is B. Clearly, the answer is B, D, E, F, G, H. Okay. We will try to solve this via. We'll try to do memorization in this. I mean, the tabulation and memorization actually yield the same result. I will just show you how you can do memorization. Okay, so let's just remove this part of the code. This part. Okay, so that's how first we can get t1 dot size, t2 dot size. Is my transition correct? Where have you mentioned any transition? You just said we should use 2D DP. Your guess is correct. We'll be using 2D DP in this problem. Return. Let's create an helper function which will give us the answer for this problem. So it should be int help int I comma int j string if I less than 0 or j less than 0, return 0, because there cannot be any common subsequence in empty string, right? uh, I mean, if I reaches less than 0 or j reaches less than 0, that means s1 is empty or s2 is empty. uh, mm, if t1i equal to t2j, then you simply return 1 plus help of I minus 1 comma j minus 1 comma s1 comma s2. And if not, then you return help of I minus 1 comma j s1 comma s2. Actually, you have to return max of both of them, max help of I comma j minus 1 comma s1 to return this. Let's see, looks correct. Oops. Use of undeclared identifier t1. Oh, it should be s1. Oh. Let me just make everything in terms of t. T. Okay. This should give time limit exceeded error. I mean, it should give time limit exceeded. Yes. So you simply memorize it by the number of states. There's a simple trick you use in memorization. dp of n comma vector of. It's quite similar to the tabulation. Now this should accept. Yep, now it accepts. So that's how you solve longest common subsequence. So today we did a problem on minimum path sum. Then we saw how to solve longest increasing subsequence, which looks like 1D DP but is solved by 2D DP. There we finished the patterns for subsequences, and now we have solved a problem involving DP on strings. So DP on strings, the core idea is you take two pointers, I and J. I and J denote a point of a string, and then you, according to the problem, you try to modify that string according to the problem. I will give you one homework problem, uh, longest palindromic subsequence. It's a very important problem. Um, you can solve it before the next session. We will discuss it before the next session. I apologize for the network error in today's session. Um, you can try to solve this problem. We will discuss it in the tomorrow session. We will meet tomorrow at 7 p.m. You can read it. And if you have any doubt, then you can stay. Otherwise, the session is over for today. Today is also lead codes bi-weekly, so you can go and solve it. You can go and participate in the contest. Try to solve this problem before coming to the next session. I think there is no doubt to anyone. Then we will discuss this problem. Then we will jump onto the graphs, and we will discuss about many other algorithms based on graphs. Okay. See you all in tomorrow's session. Okay, Arpit has shown transitions. Yes, Arpit, it looks correct. Your transition functions are correct. I guess I missed them in the chat. Okay, okay. Welcome, welcome. Bye bye. See you tomorrow at 7 p.m.